Hi, my name is Martin Avanzini, and in this short video I give you an overview on our work on continuation passing transformations and expected cost analysis. This is joint work with Gilles Barthe and Ugo Delago. So in this work we are interested in a resource analysis of programs. Such a static resource analysis is a well-established research field where a lot of different techniques have been proposed. However, most of these techniques are confined to sequential models of computation. On the other hand, if we look at application areas such as, for instance, cryptography or robotics, then the underlying model of computation is inherently randomized. This motivates us to look at probabilistic programs in the sense of ordinary programs that have some source of randomness built in, for instance through the use of sampling-in structures. A computation should then really be conceived as a stochastic process that ends up in a distribution or sub-distribution of possible outcomes. Concerning cost or resource analysis, it's very natural to assign a unitary cost to certain primitive operations and then define the cost of a computation simply as the accumulated cost of all the operations that have occurred. Now, in a sequential setting, we would be interested in maybe in finding an upper bound to this cost function. In a probabilistic setting, the cost itself of a computation is a random variable, so morally it depends on the random choices that have been performed in this computation. What we will now be interested in is to find an upper bound to its expectation, so to the mean value of this random variable. To make this a bit more concrete, let's look at an example. In these boxes of serials, you have 1 out of 6 actual figures. Now you may ask yourself how expensive is it really to collect all these actual figures, and a good way to reason about this one may be to look at how many boxes of cereals you have to buy on average in order to receive all these 6 actual figures. This is an instance of the so-called coupon collector problem, which is modeled by this small probabilistic program here drawn above. So this function coupons takes a list of all coupons that could, for instance, represent the actual figures 1 to 6, and then simply iterates by collecting new coupons by drawing uniformly at random a new coupon from the list of all coupons and adding it to the collection that we already own. So on the surface this is an ordinary functional program. However, we consider 2 additional constructs. The first construct is this tick here, which is our way to impose a resource model on such functions. It essentially tells you to consume now 1 resource unit, and we have sampling-in structures like this draw procedure here, for instance. Now if we look at the evaluation of this function, for instance, with coupon number 1 and 2, then we could be very lucky and after 2 iterations, so with cost 2, collect all the 2 coupons, or we could be unlucky and never finish collecting coupons. However, on average, the number of draws that we are performing can be shown to be bounded by this expression here. Okay, so if we come back to the example of serial boxes, n is the number of coupons. If we substitute 6 here, then we see that on average 14.7 serial boxes have to be bought in order to collect all these coupons. And the question we are asking now is, how can we formally derive such bounds? There has been actually a lot of research going on into this direction, but most of the works are confined to imperative probabilistic programs. Just recently we see some novel techniques, among them also work by us, that makes use of type systems to reason about the expected resource usage of functional programs. The problem with this approach is that it's very difficult within a type system to capture probabilistic effects at the same time in a concise and precise way. The implication of this one is that when you design such a type system, you will have to make a trade-off between the expressiveness of the type system and the way how difficult it is to reason within this type system. Now, another approach generally to resource analysis goes back to the work of Wakebright of 1975 that makes use of program transformations. So in his work, Wakebright considers functional programs and extracts from these functional programs in a systematic way a cost function. Now, this cost function itself is again expressed as a functional program, which allows us now to use conventional tools for program correctness to also reason about the resource usage of programs. The approach that we are proposing for probabilistic programs falls precisely within this framework. We start from a higher order functional programming language endowed with sampling operations from discrete distributions and these cost annotations through ticks that we have seen for an example. And on this we apply our expected cost transformer that extracts from this program in a systematic way an expected cost function. And crucially, this expected cost function is represented now as a non-probabilistic program. This means now, again, we can use conventional tools from static analysis to analyze the image of this transformation in order to reason about the expected cost of our probabilistic programs. So this picture sums up our two main contributions. On the one hand, this cost transformer, and on the other hand, an adaptation of a higher order logic to reason about such cost functions. Now, this expected cost transformer is actually inspired by the expected runtime transformer of Kaminsky and others, defined in 2016, that gives a sound and complete methodology for reason about the runtime of imperative programs. The idea is that this cost transformer transforms to a cost of a continuation to an overall cost. So it will yield a positive real number or infinity in case the overall computation has an unbounded cost. Now, what we realized is that on the pure fragment, this cost transformer is simply an instance of the one-pass continuation passing style transformation that you find, for instance, in the literature by Danby and Nielsen, which gives the name also to our paper. The crucial aspect of formalizing this transformer in a continuation passing style is that we now can extend this notion very seamlessly also to our impure fragment of the language. Whenever we see a tick term, we just add 1 to its expected cost, and whenever we see a sampling instruction, morally what we are doing is we simply compute the expectation, so the mean value of the cost of this continuation kappa with respect to the sampling operation that we are performing. Possibly also first evaluating the arguments m to this sampling instruction. To make this a bit more precise, if we, for instance, transform cost of a continuation kappa with respect to a unbiased coin flip that is tick, then this amounts to 1, accounting for the tick, plus kappa applied to head and tail respectively, both of these probabilistic choices weighted by the corresponding probability 1/2. So on our coupons example, this transformation results in this function here depicted to the right. It's structurally identical to the original function, just in addition it takes a cost of a continuation k as argument, and the tick and the probabilistic sampling structures are resolved correspondingly. Now, the cost of this coupon function itself we can now express in terms of this CPS version, where we instantiate the cost of the continuation as the constant zero function. Now, of course, because these two programs are structurally similar, and the first program is potentially non-terminating, so is also this cost function defined as we have done so here. So this cost function evaluates to such an infinite tree, and what we can show is that the cost defined in this way converges precisely to the expected cost of the initial program. So far so good. We have now a functional representation of the expected cost of our probabilistic programs, and what we would like now to do is to find a closed expression for the so-defined cost function. And to this end, we make use of an adaptation of the higher order logic. So this higher order logic that we are introducing is a formal system for deriving judgments of this form. Morally, they are annotations of an ordinary type judgment with assumptions on the environment and a conclusion on the result of evaluating such a term. In addition to our type system, and this again is a crucial aspect, it allows us to reason about the converging behavior of non-terminating functions. As a small example, consider this recursively defined function. It's defined so that it converges to this infinite sum here. And crucially, in our system we can reason about such converging functions in an inductive way, where we can use the conclusion of our judgment also as an inductive hypothesis, morally. Of course, for this to work out, we have to put some restrictions, and the restrictions that we are putting is that we allow only certain predicates for reasoning about such terms, precisely the so-called admissible predicates. In particular, this enforces some notion of continuity, so that we can reason about the limit of a continuation on these predicates. The practical implication is that we can reason about upper, but for instance not at lower bounds of such functions. Okay? So what you have seen in this short talk is how we use a CPS transformation to turn the cost of a probabilistic program into an extensional property of the pure program, which enables an average cost analysis through more or less conventional static analysis tools. This encompasses the aforementioned ERT calculus of Kaminsky, but is also capable of reasoning about higher order functions. As a side note, using this methodology we can also reason about pre-expectations. Concerning future works, we really would like to have our system integrated into a proof assistant with partial automation. We would like to also be able to reason about lower bounds and non-monotone costs, which are currently outside our framework. Thank you very much for your attention, and I'm happy to answer your questions.
Hi, I'm Emmerich, and it's my pleasure to be here today to present our most recent work on STEEL, a proof-oriented language embedded within F-star based on concurrent separation logic. Over the past decade, rich, highly expressive concurrent separation logics such as FCSL or IRIS proved their usefulness to reason about complex concurrent programs. And today, we will rely on STEEL Core, a concurrent separation logic that we presented at last year's ICFP. STEEL Core has many features that you expect from state-of-the-art concurrent separation logics. It is an impredicative logic which provides all the standard separation logic connectives such as star, magic wand, conjunction, or quantification. Its memory model is based on partial commutative monoids, and it also supports reasoning in a style akin to implicit dynamic frames, while also enabling the use of dynamically allocated invariants in concurrent programs. But one additional interesting point is that STEEL Core is a foundational CSL shallowly embedded in F-star, and therefore it directly applies to dependently typed F-star programs and enables the use of powerful F-star features such as refinement types or metaprogramming, while also providing for free F-star SMT-based automation to reason about programs. So all this sounds great in theory, but unfortunately, in practice, actually using STEEL Core for verification is challenging. And to present some of the issues we encountered, I'll use this simple swap program as a running example throughout this talk. This program is fairly textbook. It relies on the standard points-to separation logic assertion to specify that initially we have two disjoint references R1 and R2 pointing to two values V1 and V2. And after execution, the post condition here specifies that we have two valid disjoint references, but the contents have been swapped. See that R1 now points to V2. So what are some of the problems we encounter when trying to write and verify this program? Well, first, doing this directly in STEEL Core requires explicit applications of the separation logic frame rule here at each function call. Second, it also requires explicit separation logic reasoning, for instance here applying associative commutative rewritings to a separation logic context through calls to the lemma commute star. And lastly, despite STEEL Core having support for implicit dynamic frames reasoning, they interact very badly with F-star's SMT-based automation, and we didn't manage to use them even on this simple swap program. And we'll come back to the reasons behind this a bit later, but for this swap example, this forces us to use the additional ghost variables V1 and V2 here passed as arguments. So instead of all this, we would much rather be able to write the program on the right, where all these issues have been solved. And so in today's talk, I will present the different steps that bring us from STEEL Core to the STEEL language and enable us to write this much nicer swap program. So to solve these issues, our contributions are the following. First, we propose a type and effect directed frame rule, which makes applications of framing algorithmic. We then automate frame inference itself by encoding the problem as an associative commutative unification problem modulo theories. And we provide a partial decision procedure for it that relies on a cooperation between F-star tactics and SMT solving. To improve the usability of implicit dynamic frames, thus removing the need for ghost variables in swap, we show how to automatically separate verification conditions between separation logic and what we call selector predicates, which are easily encodable to SMT. And finally, building upon all this, we demonstrate the usability of STEEL through many verified dependently typed libraries, ranging from AVL trees relying on Viper-style permission accounting for verification to dependently typed message passing concurrency, which relies heavily on PCM reasoning. So our first step to make STEEL Core usable is to make separation logic reasoning more palatable. And one natural idea, especially when working in F-star, would be to automate separation logic reasoning by encoding it into existing SMT solvers. But unfortunately, despite their support for many logical theories, SMT solvers are not well equipped to handle separation logic. And there are several reasons to that. The first one being that separation logic is inherently higher order. Separation logic predicates are heap predicates, which are combined using different operators such as the separation logic star. Second, many separation logic predicates are recursive, and this is the case, for instance, of predicates modeling data structures like lists or trees that need to be packed and unpacked during verification. And lastly, and perhaps more importantly, the separation logic star is associative and commutative, and as such reasoning heavily relies on AC associative commutative rewritings, for instance to prove that P star Q star R is equivalent to R star P star Q, which is something that SMT solvers struggle with. So all of this seems to suggest that SMT solvers should not be used inside separation logic-based frameworks. But SMT solvers are invaluable for concrete program verification to reason about arithmetic or F-star refinements, for instance. So the question becomes, how can we combine the two when working in a rich, higher-order concurrent separation logic? And so our solution proposes to structure verification conditions to enable a cooperation between SMT and tactics, using each of them to the best of their ability. So one of the first problems we encountered is related to the frame rule at the core of separation logic reasoning. This rule states that given a separation logic Hort triple here in the premise, we can always add a frame P as long as it is separated or starred from the specification in the Hort triple. But unfortunately, applications of this rule are non-deterministic. It can be applied to any command C, creating each time a new frame P that needs to be inferred, as symbolized by the question mark. When doing interactive verification, that's fine, as the programmer can apply this rule when needed and instantiate the frame manually. But for semi-automated verification, that's more problematic, so we need to make this rule deterministic. And the way we do it is by making it syntax-directed, applying it exclusively at function calls. And you can see that, compared to the version above, here the conclusion of the rule does not contain a generic command anymore. It limits its application to function calls only. Unfortunately, directly encoding this syntax-directed rule into F-star is not possible. And the reason is that we are working with a shallow embedding of a CSL, which means that we reuse the F-star syntax and typing rules and cannot redefine function calls, for instance. So instead of making this rule syntax-directed, we leverage F-star's effect system to make it type and effect-directed. And the way we do that is we define two different modalities which correspond to computations already framed and to computations not yet framed respectively. And you can see here that the typing judgment in the conclusion of our frame rule corresponds to a framed computation, since we just added a frame. And in the paper, we present a full calculus for separation logic using these modalities, and we also proved that the logic with this new frame rule was as expressive as the standard logic with non-deterministic framing. And so, to actually encode this calculus into F-star, we relied on a recent F-star feature called indexed effects, which extends F-star's effect system and allowed us to encode the different modalities as different effects. So now that we automated applications of the frame rule, one problem remains. We must automatically infer the frames created, that is, the terms that were prefixed by a question mark. And let me explain how this works in STEEL on this simple example, which performs two successive writes on the reference R1. So first, the frame rule is automatically applied to both function calls, generating the frame F1 for the first call and F2 for the second call. So now we need to solve F1 and F2. And our observation is that separation logic verification conditions can be seen as associative commutative unification problems. For instance, solving the VC pointer R1 star pointer R2 is equivalent to F1 star pointer R1. That corresponds to finding a unification solution for F1 while allowing AC rewritings on the star. And the second observation is that we can always solve the equivalences in an order such that each problem contains at most one frame metavariable. And one way to do so is by simulating a forward symbolic execution. So starting from the top of the program, we solve F1 in the first problem encountered, then F2 in the second, F1 having been solved just before, and we finally reach a problem where no frame metavariable remains. And importantly, thanks to our restrictions on the application of the frame rule, the observations made on this simple example actually hold for all STEEL programs, and we can apply this methodology generically. So, based on what we just observed, we therefore reduce the problem of frame inference to solving equivalencies of a shape F star P1 star P2 is equivalent to Q1 star Q2. And to solve this well-defined and well-structured problem, we define a AC unification decision procedure which we implement as an F-star tactic, ensuring its correctness with respect to F-star's type theory. And importantly, this decision procedure can cooperate with the SMT solver by querying the solver to determine equalities on subterms leading to AC unification modular theories. So for instance, here in this simple example, the AC unifier can pass the equality V1 equals V2 to the solver and conclude that the two terms are equivalent if the solver determines that the equality holds. And lastly, our decision procedure is partial, but in exchange, it does not require any backtracking. And since we are inside an interactive proof assistant, the user can always help frame inference by providing annotations. So as such, our tactic sacrifices completeness for speed and user interaction, enabling practical automation for separation logic reasoning. So we provide the full details of the decision procedure in our paper, including a proof of termination of the decision procedure and a proof that the scheduling we presented in the previous slide always exists for steel programs. So through its different steps, our hybrid tactic and SMT-based program verifier eliminates all mundane proof steps related to framing, yielding the program here on the right for swap. And you can see, for instance, that manual calls to the frame combinator or to AC rewriting lemmas disappeared. But the last annoyance is the presence of these ghost variables V1 and V2. And I will quickly show next how we can remove them in steel, providing a style akin to implicit dynamic frames. So the main challenge with combining separation logic with heap predicates in the style of implicit dynamic frames is that, to be sound, heap predicates must be self-framing. That is, they can only depend on the part of a heap corresponding to the separation logic context. And this self-framing requirement is quite complex to reason about. It is higher order and interacts very badly with SMT. So to solve this issue, we instead propose a new notion of selector, which corresponds to a self-framing representation of a separation logic predicate. So for instance, the selector of a reference could be the value it contains in memory. And building upon this, we propose a new formalism based on quintuples, where P and Q are separation logic assertions, and R and S are selector predicates. For instance, R is a proposition that can only access the selector of P. And selector predicates are therefore self-framing by construction, and we can abstract away the complex self-framing requirement from the user and the solver. So first-order logic selector predicates, for instance, relating reference values in swap, can then be easily encoded to SMT. And in the paper, we provide the full calculus using quintuples and prove it sound with relation to steel core. So through all these steps, we obtain the swap program here on the right, where framing and frame inference have been automated, and where we can specify the functional correctness of swap using selector predicates. And so this works with a wide range of programming idioms, and in the paper, we show that it heavily reduces the proof overhead, and also present many examples ranging from AVL trees to standard concurrent data structures, as well as a PCM-based encoding of two-party dependently tagged sessions. So in conclusion, we presented today steel, a full-fledged proof-oriented language for concurrent programming, which is shallowly embedded in the dependently tagged F-star, and is based on a foundational CSL called steel core, which is entirely mechanized in F-star. Despite its expressiveness, steel provides useful automation facilities by relying on a mixture of tactic and SMT solving, while supporting many styles of specification and proof for concurrent programs, ranging from a Viper-style permission accounting with implicit dynamic frames, to Iris-style dynamically allocated invariants, while also including partial commutative monoid-based reasoning and dependent types. And we are very excited to push this verification framework to its limits, to reason in future about complex, low-level, high-assurance concurrent programs. Thank you for your attention.
Hi everyone, my name is David, I'm a student at Carnegie Mellon, and I'm going to be telling you about some work between me and my co-author Jan Hoffman that we call Automatic Amortized Resource Analysis with the Quantum Physicist Method. But first, let me make sure I tell you what this work is not about. Despite having quantum in the name, this work does not involve quantum computing, or any actual quantum physics at all. With that out of the way, what this work is about is analyzing programs to determine their resource usage, like how much time, memory, or energy they will take to run. And we want to do this in terms of the size of the program's input. One particular way of performing this kind of analysis is called the Physicist Method, because it metaphorically bookkeeps resources as if they were potential energy. You can imagine storing some amount of potential energy on each piece of an input data structure, like our list here, and paying from that store like a wallet when costly operations are performed. The total amount of energy on the input list would then give a bound on the total resource cost. This not only lets us reason about resources like time, which just monotonically tick down, but also resources like stack, which non-monotonically are allocated and freed, going up and down. The first resource, time, is easily measured with net cost, the change in energy. The second resource, stack, is better described with the high watermark of cost, the maximum amount of resources in use at a given time, which here is simply how much energy we need to start with to not go negative. The goal of the Physicist Method is figuring out how much energy to start with and how much to pay out over time. Right now, let's start by showing how the traditional Physicist Method reasoning works. Here we have a typical length function for a list. If we want to reason about how many call stack frames this might use, then we just need to count the number of recursive calls. In this case, it is easy to see that the number of recursive calls is equal to the length of the input list. Now let's use the Physicist Method to figure this out mechanically by trying to assign some amount of potential per element of the input list. So let's set it up with our input list having 1 unit of energy per element. From here, the manipulations of potential occur in lockstep with our program. When we perform a pattern match, we free 1 unit of energy and keep a tail list with the same energy density as the original input. Then we come to the recursive call. And here, it turns out that we are perfectly set up to pay 1 unit of energy for the call stack frame and provide an argument with the proper energy density for the recursive call. Thus, inductively, we can conclude that the amount of energy we started with, 1 unit per element in the list, is an upper bound on the amount of call stack frames needed, which is exactly the bound we wanted. And this particular example also shows how we can use the Physicist Method in a type system by wrapping the amount of energy into the type of the list, which we do with the yellow superscript here. This also lets us type the function len like this, as taking a list with 1 unit of potential per element and 0 extra units, and returning an integer with 0 extra potential. This type system is called Automatic Amortized Resource Analysis, or AARA, and it can automatically perform the reasoning we just did to find resource bounds by reducing the problem to linear programming. Now, this is great, but there are common patterns where it gets into trouble. Here we see the size function. It is like the length function we just went over, but it gives the number of nodes in a tree instead of a list. If we again want to measure the number of call stack frames needed, the problem becomes a little more complicated. You see, we make 2 recursive calls, and because they occur sequentially, we can reuse the stack from the first call for the second. As a result, the number of stack frames needed is the depth of the input tree, not the number of nodes. However, if one naively uses the Physicist Method, like AARA, one only finds a bound equal to the total number of nodes, given by this function type, with the superscript 1 indicating 1 unit of potential per node in the input tree. There are multiple reasons for this type's poor resource bound. The first is a shortcoming of AARA. Its types do not track leftover potential very well. If you look at the function type, there is nothing to indicate that all input potential is also returned, so there's no way to reason about the reuse of such potential. Now, we do solve this problem in the paper, but this will not be the focus of the talk. The second problem is a shortcoming of the naive usage of the physicist method, which would assign potential locally as a fixed function of each data structure. You see, even if we did solve the first problem and had potential to reuse on the subtree T1, there is no transfer operation to give that potential to the subtree T2. From the time the variable T2 is bound at the pattern match to the time it is given as an argument, T2 is untouched. So neither its type, nor structure, nor anything else about it has a chance to change. The naive physicist method is therefore forced to keep its potential equal to when it was bound, and cannot add in the potential from T1. Now, while this rules out the naive physicist method with locally defined potential, there is still an option for a more sophisticated global approach that takes all data structures as arguments simultaneously, even those that are not being operated on. This is where our work on the quantum physicist method comes in, showing how to derive such a globally defined potential function in a principled, structured way, enough that it can even be automated. And with such a non-local potential function in hand, normal physicist method reasoning can apply. To show the workings of the quantum physicist method, I'm now going to walk through how they work in a setting outside the type system of AARA, so that we don't get too bogged down in notation. Imagine that there are $5, and we give these $5 to Alice and Bob to share. And Alice and Bob are going to go to the candy store and use this money to buy some candy. In particular, let's say that Alice wants to get some Crunch Bars costing $3 for the pack, and Bob wants a Kit Kat costing $2. These costs add up to $5, so it is beginning to look like the way they should split the money should be obvious. Alice gets $3 and Bob gets $2. And this is exactly how the traditional physicist method would reason. That would be the end of the story if not for one more wrinkle. You see, here's the twist. While Bob can just pay for his candy directly, Alice's Crunch Bars are in a vending machine that only takes $5 bills. If we did nail down that Alice gets $3 and Bob gets $2, then Alice could never get her candy because she couldn't use the vending machine. Note that this temporary requirement of $5 is kind of like a potential barrier in physics. Anyway, despite the barrier, there is still a way for Alice and Bob to both get their candy, and it's exactly the way I used to split money with my little brother growing up. We start by having Alice hold all of the $5. She then puts that $5 into the vending machine and buys her candy. She then gets back the $2 in change. This $2 she can then give to Bob, and finally, Bob can buy his candy. What an elegant solution! However, while this solution is very nice for Alice and Bob, it makes our bookkeeping using the physicist method a little harder, and the problem is this step right here, where Alice transfers money to Bob. You see, while the physicist method can do this bookkeeping, it requires an explicit transfer between Alice and Bob to work smoothly. But, as we've already discussed, this isn't really something we want to track. These kinds of transfer operations just do not exist in real code. To deal with this problem, we are going to change how we think about the way that Alice and Bob split their money. Let's look at how they might do it. They could split it $5, $0, Alice could give $3 to Bob, Bob could give $2 back, and so on. Alice and Bob are not adversarial, so they can cooperate and split the money however is most beneficial at any given time. So, rather than fix any one split of the money, we are going to consider a sort of cloud of all the possible splits at once. This is our collection of worldviews, where each worldview tracks a different allocation. By using many worldviews at once, we simultaneously consider whatever relevant ways the money could be split. In one worldview, Alice holds all the money, in one Bob does, and so on. And by representing these many realities simultaneously, this behaves a little like quantum superposition. Now, let's show how this cloud of worldviews enables non-local reasoning in our bookkeeping. This is going to use a principle we call resource tunneling, which builds off of our worldview superposition to get something analogous to quantum tunneling. To do so, we are going to look at these two worldviews in particular, where they split the money $5, $0 between Alice and Bob, and where they split it $3, $2. We are now going to see what happens as we bookkeep our desired solution, where Alice gives Bob the change. The first major principle in this bookkeeping is that every worldview pays the net cost of whatever operations occur. So, when Alice pays into the vending machine, this is the resulting allocation in each worldview. You will now notice that in the second worldview, Alice has negative money. This is usually nonsensical, but we are going to allow it right now, as long as the second principle of this bookkeeping is satisfied. That is, there always exists a worldview that covers the high watermark of resource usage, which would be a worldview where our money never goes negative. You see here, the first worldview satisfies that principle. And now we see the step where Alice gets her change back, still adhering to our two principles. And finally, we see the step where Bob pays. Now, because we've kept to the two principles along the whole way, we can construct a path through our worldviews like this. Notice that this is exactly the same sequence of money allocations as our desired solution. But now the transfer of money between Alice and Bob happens implicitly at the dotted line. There, the transfer is encoded by the path simply jumping to a worldview with a different allocation of money. And each step along the way, we have real, non-negative amounts of money. In fact, no matter the scenario, as long as we follow our two reasoning principles over these worldviews, such a path like this always exists, where money is non-negative and where transfers are encoded implicitly as jumps between differing worldviews. Now, let's go back to our previous code example. By using the updated AARA-style type system in our paper, we can assign the following type. This type differs from the previous in two ways. Firstly, we use a subscript on the tree type to indicate 1 unit of depth potential. And secondly, we include this additional term at the end to indicate how much potential is returned on the input data structure. So, what this type says is that our tree traversal only requires stack equivalent to the depth of the input and gives it all back at the end, which is exactly the bound we want it to get. And this type is justified by a type system using the quantum physicist method. Just briefly showing some bookkeeping, you can see this spot in the middle, where the circles jump from left to right, implicitly shifting potential from the first subtree to the second, exactly as we need it. Now, in the paper, we go over all the features of the quantum physicist method in detail, like showing how to extract an explicit potential function out of it. We also automate the reasoning using the AARA-style type system, and prove the whole system is sound, so you can in fact trust the reasoning going on here. We also apply this type system-based analysis to the OCaml standard library set module, which implements sets using trees. We show experimentally that this can indeed reason better about things like stack and tree depth, allowing for the inference of much tighter call stack bounds than AARA could previously provide, with only moderate overhead. You can see some of the results from our paper here, but to summarize, our implementation never finds worse bounds and finds strictly better bounds over 30 different functions in the module. And with that, I'll conclude my talk.
Hi, and welcome to this talk. I'm Armel Guénaud, and I'm excited to be presenting the work done with my co-authors on obtaining theorems for free from separation logic specifications. You might have already heard about this idea of theorems for free from the work of Reynolds, Plotkin, and Wadler in the context of polymorphic types. There, the idea is that if you know that some program has a given type, for example, for alpha, alpha, arrow, alpha in system F, then whatever this program might be, you can get a free theorem about the behavior of the program. For example, here, that it is actually contextually equivalent to the identity function. And this kind of equational property is a free theorem in the sense that it holds of any program of the type, just by looking at the type. In this work, we applied this idea of theorems for free in the context of separation logic specifications. Intuitively, for a library that satisfies a given separation logic specification, this specification restricts the way the library functions can be called. And thus, it can be understood as defining a set of legal traces of interaction between the library and a client. We show that this intuition can be made actually precise, and that we can thus obtain theorems about the interactions between a client and the library, depending on their specification. Let us consider a concrete example. So here we have a separation logic specification for a minimal file library giving access to a single file. Initially, the specification gives us the closed separation logic resource, which specifies that the file is initially closed, and we also get the specification for three operations. The open function opens the file, consuming the closed resource and producing the open resource. Read leaves the file open, and finally close consumes the open resource and gives back the closed resource. These open and closed predicates are abstract, so a client of the specification can use them as abstract token but cannot unfold their definition. Then it seems quite clear that a verified client will not be able to call the functions in any order. In fact, any client will call the functions in an order that corresponds to the automaton shown here on the right. And this is a property that I will show how to prove formally later. It might seem fairly obvious at that point, but it's important to note that it does not follow from any standard model of separation logic, so we'll have to do something more. Then we can consider more expressive separation logic specifications, which enforce even more interesting interaction traces. So consider the specification for a library of mutable collections. We have operations add and remove, which modify the collection in place, an operation iterator, which produces an iterator on the collection, and a function next, which can be used to get a new element from the iterator. Now, this specification is quite expressive. And indeed, a maybe seasoned practitioner of separation logic can look at it and say, yes, I can see that this specification prevents iterator invalidation. And, well, indeed, add and remove generate fresh collection identifiers, while next requires an iterator and collection with matching collection identifiers. So it does follow that for any client of the library, an iterator is only used with next as long as the underlying collection has not been modified with add and remove. What we provide is a formal framework for establishing this kind of results. That is, deriving free theorems as trace properties of client-library interactions from separation logic specifications. And we apply this approach not only to reason about challenging sequential specifications involving iterators, higher-order functions, specifications relying on well-bracketing protocols and full functional correctness, but we also show that it scales up to allow reasoning about concurrent library specifications, for which we prove the general result that logical atomicity entails linearizability, and so more on that later. And finally, the whole work has been fully mechanized using COC and the IRIS framework. So what was the challenge? Well, the main challenge was in fact in finding how to even state formally the free theorems that we want to obtain. In the case of parametricity results for types, free theorems are formulated as equational properties relying on contextual equivalence, which is itself easy to define on top of standard operational semantics. In the case of separation logic specifications, however, we wish to prove a different kind of properties, namely trace properties about calls and callbacks between client and library. And for that, we have a problem, which is that these interactions are not easily observable. Indeed, the distinction between client and library is first really only exists at the logical level. At the level of the operational semantics, after library and client have been linked together, the calls between the two simply become indistinguishable from other reductions of the program. But we can try anyway to write down formally the shape of a free theorem and see what the problem is. So what we would write is that we consider some library lib satisfying a specification phi, a client verified against phi, and then when those are linked together, they should interact as described by phi. The first part sounds okay. Indeed, the theorem should still hold if we swap in a different implementation for the library or the client. But the second part is clearly no good because it's still too informal. So what can we do? Well, the key idea of this work is to add a spy. So instead of directly linking the library with the client, we will implement an additional piece of code W, which acts as a wrapper on top of the library and is going to spy on its interactions with the client. The wrapper assumes a library satisfying specification phi, and itself implements the specification phi. So from the point of view of the client, the wrapped library is indistinguishable from a normal library. But additionally, every time there is a call between the library and the client, the wrapper will record that this call has happened by emitting an event which gets recorded in the global trace. So the recipe is as follows. Given a specification phi, we first implement a wrapper that observes the call between library and client. And then we will prove that the trace of events emitted by the wrapper satisfies some trace property of interest, big L. And L can be, for instance, the language for the automaton we saw earlier. And if we do these two first steps, then we obtain, as a free theorem, that for any library implementing phi, for any client verified against phi, when we link together the client, the wrapper, and the library, then for any number of reduction steps, the trace of events that are emitted satisfies the property L. Now, on a more technical level, we need in the wrapper code to be able to emit these events I just mentioned. So we extend our otherwise standard programming language with a new emit primitive to emit an event. And we also extend the values with labels, which are just strings that can be used to identify different events. Then the semantics of emit v is simply that it reduces to unit while emitting v as an event, and a trace is simply a list of values. As we will use separation logic to reason about the behavior of a given wrapper, we also extend our separation logic with predicates to talk about the trace. There are two of them. The predicate trace t asserts that the current trace is exactly t. And then the predicate trace inf of L asserts that at any step, the trace must satisfy the trace invariant L. And then these predicates allow formulating a rule for emit, which requires proving that the new event which is being emitted preserves the trace invariant. Now, let's make things more concrete. We can come back to the specification for the file library we have seen earlier and see how we can apply our recipe for free theorems. The specification is the same as before. Then we define our wrapper program, where each instrumented function simply calls to the library function and then emits an event with the corresponding label. Then the trace property that we expect of these emitted events is given by the automaton we've already seen. Formally, we write LC for the language corresponding to the state where the file is closed, LO for the language where it's open, and LFile, the trace property, as the union of the two. Then we need to actually verify our wrapper. And we prove that, assuming some library lib satisfying the file specification, and given separation logic resources for the event trace, then the wrapper also implements the file specification. And notice that with this trace inf resource, we specify that our language L file should act as the trace invariant. Then there are two steps to the proof. First, recall that the definition of phi file starts with there exist abstract predicates open and closed. So we can actually choose what we want to use as predicates open and closed for our wrapper, depending on the closed and open predicates for the lib. And we define open as holding the open predicate for the lib, plus the fact that we have access to some trace T in LO, the language for the open state of the automaton. And similarly for closed, we have a trace in LC. Once those are defined, we can complete the proof by verifying the specification for each instrumented function. For example, for open, we need to show the following triple. And then the first step of the proof is simply unfolding the definitions. Then we apply the specification for the underlying open, which turns close to open. And finally, we have to justify the emit with the open label by showing that the trace invariant is preserved and that the trace indeed goes from belonging to language LC to language LO. And this holds because we have a corresponding transition in the automaton. Finally, as per the recipe, we get, as promised, the same free theorem as was written before, instantiated with our specification, trace language, and wrapper code. While the file example is sequential in nature, interestingly, we can apply the same approach for reasoning about much trickier properties that arise in a concurrent setting. A library which exposes a concurrent operation up has to handle the fact that this operation may be called at the same time in different threads. So to specify what it means for such a library to behave well in that scenario, the notion of linearizability has been widely used, where a library is said to be linearizable if one can reason about it as if the operation were called in a sequential fashion. In other words, one should be able to shrink conceptually the time span of each execution around a single so-called linearization point, while still observing the same results. And because linearizability is a very explicit property about the execution trace of the program, a different concept called logical atomicity has been used in some advanced separation logics to express linearizability, but in more logical terms. And the idea then is to use a different kind of special triple to specify concurrent operations, which guarantee that the operation will update in one step the resources in the precondition into the one in the postcondition. And it was understood informally that logical atomicity was indeed expressing the same thing as linearizability. Well, in this work, using the approach I just presented, combined with some more advanced separation logic proof techniques, we can actually prove formally as a theorem that logical atomicity indeed entails linearizability. And there are more details about the proof in the paper. To wrap up, I showed in this presentation how we can formally obtain three theorems about the calls between a library and a client, given a separation logic specification describing the interface between the two. We can even draw a comparison with how three theorems are obtained from polymorphic types. Where types give us equational properties, we get trace properties. For types, the theorem is free in the sense that it holds of any expression of the type. For us, it holds of any library satisfying the specification. And finally, in the case of types, the key insight one needs to come up with is in typically choosing the right relation to instantiate the relational model. In our case, it's in picking the instrumentation and the wrapping abstract predicates. If you want to know more, the Coq formalization and the paper are available online, and I'll be happy to answer questions as well. Thank you for listening.
Hello everyone, my name is Yao Li. Today I'm going to talk about our work on reasoning about the garden of forking paths. This is work in collaboration with Liao Xia and Stephanie Warwick. This talk is about lazy evaluation. Lazy evaluation, also called by need semantics, is an evaluation strategy that only computes what you need. It is the default evaluation strategy in some functional programming languages like Haskell. What's good about this evaluation strategy is that it allows the program to have better performance because you only compute for what you need. In addition, it also makes the programs easier to write and enables better compositionality in your programs. These are all good. However, all these good things do come with a price. In particular, lazy evaluation makes the performance of the program hard to understand or reason about. Let me elaborate with the following append function defined in Haskell. My question is, how many calls of append would happen to evaluate the following expression? A. 3 calls, B. 1 call, and C. 0 call. A hint is that this is a trick question, and the answer is that it depends on the demands on the resulting list. And depending on the demands, all 3 answers are possible. In the case that every cell in the list is in the demand, we will need to call append 3 times, so the answer is A, 3 calls. In the case that only the first cell in the list is in demand, we only need to call the append function once, so the answer is B, 1 call. And in the case the entire list is not used at all, so there is no demand, the answer is C, 0 call. To make things more complicated, we cannot know the demand of something until we use them. Let's consider the following program P as an example. Assume that we first evaluate take 1 XS. It will realize that we need the first cell in XS, so it computes the first cell in XS and stores the result in the memory. And then it carries on with the computation of P. Later, it realizes that we not only need the first cell of XS, we also need the second cell of it. So it retrieves the computation result we had earlier, computes the second cell of XS, and stores that in the memory again. In this way, the evaluation of the append function interleaves with the evaluation of the rest of the program, making the evaluation stateful and the performance cost of the program hard to reason about. In our work, instead of directly dealing with the complexity of lazy semantics, we ask the following hypothetical question. What if we know the demands beforehand? First, we note that the demand is monotone, and we note that we need the first 2 cells of the list. We can save some steps by directly compute the first 2 cells. And second, we note that the evaluation order does not matter in the performance cost analysis. So we can move the computation of the first 2 cells to the call set of XS, just like in the call by value semantics. And this all sounds good, except for one minor problem. That is, we can't know the demand beforehand. Fortunately, we can simulate this using non-determinism. So when we evaluate XS, we fork the computation into multiple different branches, each branch with a different demand. And during the evaluation of the entire program, some of these branches would result in failure because the conjectural demands on these branches are not sufficient. Eventually, one of the remaining branches would faithfully model the computation cost of a lazy program. This idea is not new. In fact, this is called the Clairvoyant call-by-value semantics. It was proposed by Hackett and Hutton at ICFP 2019. In their paper, they define the operational and denotational semantics for the Clairvoyant call-by-value. In our work, we further recognize and encode this semantics in a monad, called the Clairvoyant monad. In our work, we use the Clairvoyant monad for reasoning about the computation cost of lazy programs. Our method works as follows. First, we start from a lazy and pure functional program, and we do an automatic translation that translates the program into a monadic program wrapped inside the Clairvoyant monad. This step achieves 2 things. First, It reifies the laziness in the original program using a strict semantics. And second, it accounts the cost of the original program and accumulates that inside the monad. And after we have these monadic programs, we can use some problem logics for reasoning about the computation cost of the original program. In our work, we implement the Clairvoyant monad and the problem logics using the Galena specification language and the calc proof resistant. We do not have an automatic translator that translates a particular program language into Galena. Instead, we develop a translation strategy for a lazy lambda calculus with false. This does limit our work to some extent, as we do not support features such as infinite data structures or non-structural recursion. However, many lazy data structures and algorithms actually do not rely on those features, and our framework provides a simple way for reasoning about computation cost of those programs. The key feature of our framework is its simplicity. The Clairvoyant monad is very easy to define. In fact, it can be defined using around 20 lines of Galena code, and the program logics enables modular reasoning. Now, let's look at the first part of our method. Let's again use the append function as an example. First, we translate the append function to a function that has the following type. The first difference is that we augment all the input types of the function with a possibly undefined value. The undefined value represents that the value has not been evaluated on this branch because it is not in the demand. Furthermore, we also redefine list as what we call the approximation of a list. The approximation of a list also augments all the value inside it with a possibly undefined value. At last, we wrap the computation inside a monad, that is the Clairvoyant monad. What is a Clairvoyant monad? We can answer this question by asking, what do we want from this monad? First, we want it to be able to accumulate a computation cost inside a program. And second, we want it to be able to model non-determinism. And finally, we want it to be able to model failures in certain non-deterministic branches. And the Clairvoyant monad is the minimal implementation that implements all these three features. In fact, it is the writer monad transformer applied to the power set monad. And we can further uncarry this definition to obtain the definition as follows. We can define the following operations on the Clairvoyant monad. The first two operations are the monadic operations. In particular, band is the operation that accumulates the cost across the program. Tick operation is the operation that increments the computation cost. Thunk and force are the operations that model non-determinism. All these operations can be defined using around 20 lines of code in Galena. Now, let's look at the append function again and see these operations in action. First, we insert a tick operation in the head of every function body so that we can count the number of function calls as a measure of computation cost. Our next step is to make the function call recursive. After that, we want to do a pattern matching on the function's first parameter xs. A problem here is that xs can be undefined on some branches because we conjecture that xs is not in demand on those branches. Therefore, we apply the first operation to xs. In the case that xs is indeed undefined, first operation will simply fill the branch. In the case that xs indeed contains some value inside it, we continue on pattern matching on the value inside it. Inside the pattern matching, in the case that xs prime is not an empty list, we want to make a recursive call. Instead of making the recursive call directly, we wrap it inside the thunk operation. What the thunk operation does is forking the computation into two different branches. It discards the computation on one branch and continues the computation on the other branch. This is a key for implementing non-determinism. In this way, the evaluation of the function becomes a garden of forking paths, where different possibilities of demands are enumerated. These are the key ideas behind the clairvoyance monad and our translation strategy. In the paper, we talk about the definitions of clairvoyance monad and our translation strategy in more detail. We also prove an equivalent theorem of our semantics with respect to the semantics of Hackett and Hatton in our paper. Now that we have imposed the computation cost of lazy programs inside the clairvoyance monad, let's move on to talk about how we can formally reason about it. The clairvoyance monad replaces laziness with non-determinism, so we don't have to reason about laziness. But now we need to reason about non-determinism. Let's use the function p as our running example again. In the case that we have at least some demand for xs, the possible result of xs is shown as follows. How should we specify all the possible non-deterministic result of xs? The typical way of specifying a program is based on over-approximations. In this case, the over-approximation of xs is that the cost is in the range of 1 to 3. And we can apply this specification to reason about p. First, we note that p requires at least the first 2 cells of the list. So we can eliminate the first possibility, and then we conclude that the cost of p in terms of append is in the range of 2 and 3. But the function p never requires the third cell of the list xs, so the cost should never be 3. In this case, our specification failed to give us a fine upper bound for the cost of p. This is because, unlike the first branch here, even though we never need the third cell of the list, providing more than was in demand would not fail the program. To get a fine upper bound of function p, we also need a way to eliminate branches with redundant steps, like the third branch here. We do that by utilizing another kind of specifications based on under-approximations. That say, if we only need the first 2 cells in xs, then the cost is just 2. Each kind of specifications has pros and cons, so we use both of them in practice. In particular, we call the first kind of specifications the pessimistic ones, and the second kind of specification the optimistic ones. This style of reasoning based on dual specifications is also very similar to the reverse Horon logic and incorrectness logic. Here we show one pessimistic spec and one optimistic spec for the append function. The pessimistic spec talks about all the possible costs, including those with redundant steps. It can be vacuum true, it can give a good lower bounds on cost, but the upper bound might be coarse sometimes because of the redundant steps. On the other hand, an optimistic spec talks about some particular cases. For example, the optimistic spec we show here talks about the case that the demand is not larger than the first parameter of append. Compared with the pessimistic specs, an optimistic spec shows the existence of the case, and it cannot be vacuously true, and it shows a good upper bound on cost. These are the key ideas behind our program logics. You can find more detail about their definitions and their reasoning rules in our paper, along with some case studies on tail recursions. These are the key ideas behind our work. In the future, we would like to apply our translation strategy to tools like Haskell Coq, so we can reason about computation cost of lazy functional data structures written in Haskell. And that concludes my talk.
Hello, I'm Glenn Mebel, and today I will show you how to specify a concurrent data structure and a weak memory. Nowadays, concurrency is everywhere, and all real-world shared memories have some counterintuitive behavior. So, not only do we want to verify concurrent data structures, but we want to verify them against an actual model of memory, what we call a weak memory model. Our paper's contribution is a specification and a proof of a particular fine-grained implementation of a concurrent queue in a weak memory model, which is that of multi-core kernel. In this talk, we won't cover the proof, nor the implementation, but we'll see how to write a usable spec for it. Concurrency poses a number of challenges. We want to specify a data structure such that we allow sharing it between threads. So one challenge is with shared ownership, and as we'll see, solving this involves some form of atomicity. The operations of a concurrent data structure must behave as if they were atomic, and it's something we must specify somehow. Another challenge is with weak memory. With weak memory, you need to be explicit about how your threads synchronize. So spec must expose useful synchronizations, and often fine-grained implementations offer less synchronizations than a log-based one. We will tackle these challenges by using Cosmo, which is our concurrent program logic for multi-core kernel. Just to get familiar with notations, let's start with a non-concurrent specification. We have three operations, make, enqueue, and dequeue. We specify them using Hort triples. A triple is made of a precondition formula, a program fragment, and a postcondition formula. We have a representation predicate isQ, which asserts that Q is a memory location storing a well-formed Q data structure whose items are in order, the values in the given list. We are in separation logic, so conjunction is denoted with an asterisk, and the assertion isQ is not duplicable. Rather, it asserts the unique ownership of the Q. Now let's enter concurrency. For now, let's assume sequential consistency, that is, a program always behaves as some interleaving of its threads. We want to specify a queue which can be used concurrently. Can we simply keep the spec that we just saw? Well, this spec is still valid, but to use it, a thread needs the unique ownership of the queue, so that effectively prevents concurrent uses. And it makes sense because there is no reason to believe that the data structure is thread safe, unless we specify it. So let's consider a queue that is thread safe. To see how to reflect thread safety in the spec, let's adopt for a moment the point of view of the user. As a user of a concurrent data structure, we want to share its ownership among threads. And in a concurrent separation logic, such as Iris, we can do it by putting it in an invariant. An invariant is an assertion which holds at all times, and in which we can put whatever resource we want. Then it is the invariant itself which owns the resource, and any thread can access it. To access it, we open the invariant around the program fragment E. That is, before running E, we obtain the contents of the invariant, and afterwards we return it. Now the issue. For soundness in the face of concurrency, we can only open an invariant for at most one step of execution. This is a problem because the number of steps is a low-level implementation detail, and as a user, we have no idea whether the operation is complete in one step, and it's unlikely. So the user cannot use a queue sharing invariant around the specs that we have written earlier. But doing so will be reasonable because a concurrent queue has to be implemented in such a way that its operation look atomic to the user. For this, Iris provides us a notion of logically atomic triples, which we will denote with angle brackets instead of curly brackets. It's something we can define in the logic. I won't show how, but the key point is that we have these couple of properties. First, a logically atomic triple entails the regular triple. Second, we can open invariants around it freely. This is a way of stating that E is logically atomic, and by that, we mean more formally than there is a step in the execution of E, such that E behaves as if everything happened during that step. It is this step which satisfies the Hoare triple with P and Q, so P and Q need not hold at the start and end of E, but only just before and just after the atomic step. Because of this, we need a binder to be able to name things which we only know during the atomic step when we actually open the environment. So here, X is bound in both P and Q. Fine. With logical atomicity, let's strengthen our previous spec for concurrent uses. The spec of make does not change because we do not need it to be atomic. For NQ and DQ, we do the following changes. We replace the regular triples with logical atomic triples. We bind the Q state explicitly in the triples. And that's it. So we now have a usable spec for a concurrent Q, but that was under sequential consistency. Sequential consistency is an unrealistic assumption in the modern world, so we have to embrace weaker models of memory. A one-on-one is that of C11, and here we are interested in that of multi-core. A way of describing such models is by saying that each thread has its own view of the shared state. For multi-core camel, this has been made formal by people at Cambridge, and the reference is on the slide. And based on this, we have with Cosmo a program logic for multi-core camel. A few words about Cosmo. Cosmo is based on Iris, hence we inherit all of its features, separation logic, and so on. Its distinctive trait is that, in general, assertions are subjective. We are reasoning under an implicit ambient view, which represents the current view of the current thread, and assertions may depend on it. For instance, x points to 42, it is subjective. Maybe we see that x is storing the value 42 because we have written it, but our write has not been propagated to other threads yet, and they still see another value for x. With that said, a limitation with subjective assertions is that invariants are still available to all threads. So the assertions that they store cannot depend on the views of a specific thread. They are restricted to objective assertions. Back to our Q, recall that we want to share the Q in an invariant, so its representation predicate must be objective. And we make this objectivity requirement a part of the specs. Now, do we need any other modification to the previous spec? It is still usable in limited cases, but for the general case, it lacks thread synchronization. Let's consider an example. Thread A writes to some memory region, then enqueues a pointer to that region. Thread B dequeues the pointer. Now thread B expects to read the memory region in the state in which A has left it. But remember that we are in weak memory, so it's not because A knows it has written 3 to x bracket 1 that B knows it too. So we want the queue to guarantee that when dequeuing, B learns about all writes known by A, which is a typical release acquire pattern. This is a side effect that we need, so it must be specified. From the logical perspective, the user wants to transfer points to assertions from A to B, but as I said, points to assertions are subjective, so the user cannot simply put them in an environment, and we need something more. So it's time for me to explain how views and synchronization work in Cosmo. We have an abstract notion of views. It comes equipped with an inclusion relation. The larger, the more up-to-date. And to manipulate views, we have new kinds of assertions in the logic. First, upper OV means that the ambient view contains V. So it's the archetypical subjective assertion. And second, P at V, where P is any assertion, means P with the ambient view fixed to V. P at V is objective, even if P is subjective. These assertions satisfy several rules, in particular this one, any assertion P can be decomposed into an assertion upper O V and an assertion P at V for some view V, and conversely. That's how we can transfer P between threads. We isolate all of its subjective knowledge into a component upper O V, so that what's left is an objective assertion P at V, which we can share in an invariant. So to achieve a transfer of P, we just have to transfer view assertions, and this has a runtime meaning. This is thread synchronization. Back to our queue again, we want to say that for each item, there is a synchronization, that is, a view transfer, from the enqueuer to the dequeuer. The idea is to pretend that the queue stores the views being transferred, so there is no one view for each item, and the representation predicate now looks like this. If we recall the previous spec, it is now augmented with views, and the view transfer happens like that. The enqueuer pushes its current view into the queue alongside the enqueued item. So in the pre, we use an assertion upper OV for capturing the current view, or in fact, any portion of it as chosen by the user of the spec. And conversely, the dequeuer pulls the view that comes with the item. So it gets that same upper OV, which means that now its current view includes V. So it's really the acquire pattern. I'd like to draw your attention to something. You may wonder how this approach to specification compares with refinement. In a typical refinement-based spec, you will say something like, this queue can be used everywhere we can use a naive queue protected by a lock. But in weak memory, this spec has a shortcoming. The lock induces synchronizations between all pairs of operations, even though many lock-free queues do not grant them, because precisely we try to reduce unnecessary synchronizations. By contrast, our spec is weaker. For instance, it does not guarantee any dequeuer to enqueuer synchronization, so we can specify more implementations. To recap, I've shown several tools for reasoning about concurrent programs. Invariants are well known already. To use invariants to their full power, we need to pay attention to atomicity in specs, and for that, we have logically atomic triples. What's new is that now we want to support weak memory, and for that, we have views. My claim is that the combination of all of these tools works. Logical atomicity is compatible with weak memory, and it's expressive enough for specifying and proving fine-grained concurrent programs, while at the same time remaining quite natural to use. I've only talked about specification, but there is more in the paper. We have a proof for non-trivial lock-free queue, and this proof demonstrates the benefit of our approach, because this implementation has less synchronizations than a lock-based queue, so it's not a refinement. And by the way, at the time we were working on that proof, other people were working on the refinement proof of a very similar data structure under sequential consistency, so you can have a look at the paper too. We also have a proof of a simple client application, which demonstrates that our spec is usable. And all of this takes place in Iris, a very powerful separation logic framework, and last but not least, by the virtue of COC, everything is machine checked. Thank you for your attention.